Hello everyone, I am Mehmet Fatih Gündoğar from Marmara University. In this presentation, I will introduce our work titled Integrating rPPG-based Physiological Cues into Federated Phase Presentation Effect Detection via Stacking. This study extends our previous Federated Phase Presentation Effect Detection, or simply FPET framework, by incorporating physiological temporal information derived from remote photoplethysmography, or simply rPPG. The main goal is to improve robustness against domain shift while preserving privacy in distributed biometric settings. Here is the flow of the talk. First, I will briefly describe the FPET problem and motivation behind this study. Then, I will present the proposed approach and summarize how rPPG signals and features are extracted. After that, I will explain how these physiological cues are integrated into our federated stacking framework. Finally, I will present the experimental results and conclude with the main takeaways. Face recognition systems are widely used in authentication scenarios, but they remain vulnerable to presentation attacks such as printed photos, replayed videos, or masks. This makes FPET an essential security component. However, a major challenge in FPET is domain shift. Models trained on one dataset often perform poorly on another dataset because of changes in illumination, camera devices, backgrounds, and attack styles. Centralized learning could help, but in biometric applications, sharing raw facial data is often restricted by privacy concerns. Therefore, we need approaches that are both privacy-preserving and robust across domains. In our previous work called FastTech, we used federated learning together with vision transform-based appearance models. We combined the federated global model and local data center-specific models through stacking, which improved robustness against non-IID data distributions. However, that framework mainly relied on special appearance cues. In this new work, we extend the framework by adding physiological temporal information through rPPG. The idea is that appearance and physiology are complementary. Even if rPPG is not always strong on its own, it may still provide useful auxiliary evidence when combined with appearance-based predictions. rPPG is a non-contact technique that estimates pulse-related physiological signals from RGP facial videos. It works by analyzing subtle skin color variations caused by blood volume change during the cardiac cycle. In genuine videos, these signals may exhibit plausible physiological periodicity, while spoofing attacks often lack authentic cardiovascular dynamics. In this work, we use three extraction approaches: the unsupervised green method and two supervised neural methods, efficient fees and DFees. All of them are implemented using the rPPG toolbox. Since standard FPET datasets do not provide ground truth physiological labels, the pre-trained models on UBF's rPPG dataset is used for the inference on FPET datasets. For rPPG supervised models, no FPET specific fine-tuning is done. After signal extraction, we apply a common pre-processing pipeline. This includes linear detraining to remove slow illumination drift and bandpass filtering in the physiological range of 0.75 to 2.5 Hz. Then we compute discriminative features from both time and frequency domain. In the time domain, we use statistics such as mean, standard deviation, skewness, and kurtosis. In the frequency domain, we analyze the power spectral density, the dominant frequency peak, band power ratios, and spectral flatness. The main intuition is that genuine videos are more likely to show plausible narrowband physiological patterns, as shown in this part of this figure, while spoofed samples may produce flatter or multi-peaked spectra due to noise, display artifacts, or non-physiological periodicity, as seen here in these spoofing examples. Now this slide summarizes the proposed framework. Each participating data center contributes two types of models: a local with appearance-based model and a local rPPG-based temporal model. Also on the server side, we also have the federated global appearance model. During the stacking phase, we collect the prediction probabilities from all these models and concatenate them into an extended feature matrix as displayed in these figures as fx. A final SVM meta classifier is then trained on this matrix, so the final decision is not based on a single model. Instead, it's based on the complementary strengths of global appearance information, local appearance specialization, and local physiological temporal cues. For the experiments, we use 4 widely adopted FBET benchmark datasets: RePlayTech, MSU, MFST, Eroğlu MPU, and Cassia-FAST datasets. We evaluate the framework in cross-dataset federated settings using half total error rate, equal error rate, and area under the ROC curve metrics. The key observation is that rPPG-only models are not strong consistently enough as standalone detectors because they are sensitive to dataset conditions. However, once they are integrated into the federated stacking framework, they provide useful complementary information. As shown in the below of this table, the proposed method consistently outperforms earlier federated phase presentation attack detection baselines such as FedMA, FedPET, FedGPET, and also our previous FedStack FBET baseline in several protocols. Among the tested rPPG variants, the green method-based extension achieves the best average performance. To conclude, this work extends our previous federated FBET framework by integrating rPPG-based physiological cues into the stacking stage. Our results show that rPPG alone is not sufficient as a standalone solution, mainly because of dataset dependency and the lack of task-specific physiological supervision. However, when used as a complementary expert together with appearance-based models, it improves robustness under cross-dataset evaluation. Therefore, the main message of this paper is that temporal physiological information is valuable not as a replacement, but as an auxiliary modality within a privacy-preserving federated stacking architecture. As future work, we plan to explore richer temporal cues such as optical flow and depth-based signals, and more suitable datasets with synchronized physiological ground truth. This work was supported by TÜBİTAK under these 2 projects. Here I list the main references that are directly related to the content presented in this talk. Thank you for your attention.